Hello friends, welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 4, this is lecture 5, that is the last lecture of this module, and here we will take up numerical on estimation of runoff. So, in the previous few lectures we have been discussing various methods of estimating runoff, and we discussed Cook's method, rational method, SCS-Cumnum method, and of course we did take numerical examples while discussing these methods, but because runoff is a very important topic and the questions are always asked in various competitive examinations including GATE, so it will be a good idea to cover some more numerical examples on these methods. So, we will start with Cook's method, example 1, and for a watershed, the peak runoff rate of a return period of 30 years by Cook's method is 5 cubic meter per second. The geographic, rainfall factor, frequency factor and shape factor of the watershed are 1.15, 1.6 and 0.71 respectively. The sum of the numerical values assigned to various characteristics of the watershed is 60. Find the total area of watershed. So, that is an inverse problem where we have been given the discharge and various other characteristics and we have to find the total area of the watershed. Coming to solution, the information that is provided to us is geographical rainfall factor R is 1.15, frequency factor F is 1.6, shape factor S is 0.71 and peak flow rate is 5 cubic meter per second as per Cook's method. And the peak rate runoff rate for the desired recurrence interval and watershed location is given as, this is the formula we use, QP equals to PRFS, where R, F and S we already seen, P is the uncorrected runoff rate. So, in this case P is uncorrected runoff rate, and the uncorrected peak runoff rate by Cook's method is thus knowing this information we can calculate using this relationship P equals to QP by R Fs, and the values of QP, R, Fs and S are known. So, value of P we get is uncorrected runoff rate we get is 3.83 cubic meter per second for the given data. Now, given W, that is the sum of numerical values assigned to various watershed characteristics, and the uncorrected peak runoff rate P equals to 3.83 cubic meter per second, we can determine the watershed area using the runoff curve that is used in the Cook's method. So, if you remember, this is the runoff curve we use, where this is uncorrected peak runoff rate is related to watershed area, and then there are curves, different curves for different W values, that is some of the numerical values. Now, in this case we know W equals to 60. So, obviously we have to target this particular line, W equals to 60 line, this line, and also the uncorrected peak runoff rate value we know is 3.83 cubic. So, of course, we have to read from here 3.83 cubic. So, if we draw a horizontal line cutting W equals to 60 curve and then we draw a vertical line, then of course, we can read the watershed area from here for the given data, and the watershed area from the curve comes out to be 28 hectares, and the watershed area for which we have been given the data including the peak runoff rate estimated by Cook's method is 28 hectares as per the procedure followed. We take another example. A watershed of area 80 hectares has a runoff coefficient of 0.3. A storm intensity 50 millimeter per hectare occurs for a duration more than the time of concentration of the watershed. So, the moment we are in time of concentration, that means we are talking about the rational method. Find the peak discharge in cubic meter per second. So, we have to find the peak discharge in cubic meter per second, and this question has been taken from GATE 2019 examination. So, we know that as per rational formula, the peak runoff rate is given by this equation, QP equals to CIA, where QP is peak runoff rate in cubic meter per second, C is the runoff coefficient which we have to get from table, I is the rainfall intensity in meter per second for a duration equal to time of concentration of the watershed, and the desired return period. So, just to once again remind you that when we define I, there are two things it is correlated to. One is the duration, which should be equal to at least equal to the time of concentration of the watershed, and the other is the return period for which we want to find out the peak discharge. And A here is the area of the watershed in square meters, and as I said that we are using a straightforward relationship so that we don't have to remember the conversions, etc. Otherwise, textbooks, as I mentioned earlier also, we have formula Q equals to CIA by 36, where I and A have certain units which you have to remember. So, area of the watershed is given here is 80 hectares. So, of course, we can convert in square meter 80 into 10 to the power 4 square meters. Runoff coefficient is already given in the problem, that is runoff coefficient is 0.3, and rainfall intensity is 50 millimeter per hour, that also is given here. So, that means in meter per second, if you convert it comes out to be 1.4 into 10 to the power 5 meter per second. So, using the rational formula, because now we know C, I and A. So, obviously, by putting the values of C equals to 0.3, I equals to 1.4 into 10 to the power minus 5 and A is 18 to 10 to the power 4, we can calculate the value of QP, which comes out to be 3.36 cubic meter per second. So, for the given data for the watershed, the peak runoff rate is 3.36 cubic meter per second using the rational method. Now, we take another example again on rational method, which is example 3 for this lecture. A watershed has 1.8 square kilometers of cultivated area, 2.2 square kilometers of forest land and 1.4 kilometers of grassland area. The runoff coefficient of cultivated area, forest land and grassed area are 0.25, 0.15 and 0.3 respectively. The main drainage channel has a fall of 25 meters in the total length of 2.5 kilometers. The intensity duration frequency relationship for the watershed is expressed as I equals to 700 t to the power 0.25, where capital T is the recurrence interval in years, and in denominator we have Tc plus 15 to the power 1.4, where Tc is time of concentration in minutes, and of course I is the intensity of rainfall in millimeter per hour. So, of course, this is the intensity duration curve applicable for the area is already mentioned. For a recurrence interval of 20 years, find the peak rate of runoff for the watershed in cubic meter per second, and this question has been taken from GATE 2014 examination. So, rational formula, just to repeat, QP equals to CIA, where Q is the peak rate of runoff in cubic meter per second, C is the runoff coefficient, I is the rainfall intensity in meter per second for duration equal to time of concentration of watershed and for the desired return period, and A is the area of the watershed in square meters. So, that is what is we know about rational formula. Now, because this particular watershed has multiple land usage, so obviously we have to use the weighted runoff coefficient, and as per data we have cultivated area, forest area, grassed area. The area under each category are 1.8 square kilometers, 2.2 square kilometers and 1.4 square kilometers, and we have been also given the values of runoff coefficient applicable to these land uses, that is for cultivated area it is 0.25, for forest land it is 0.15 and from grassed area, for grassed area it is 0.13. So, obviously using the information we can easily calculate the weighted runoff coefficient, which will be used in the rational formula as sum of J12 and Cj divided by sum of the total area, where J is the number of land uses here. So, in this case it is 3. So, that is why it is 0.25 times 1.8 for cultivated area, 0.15 into 2.2 for the forest area, and 0.3 into 1.4 for the grassed area, and then we have the total sum area of the entire land, which is sum of all these three. So, using this we get a weighted runoff coefficient of 0.22, wherein we saw that the runoff coefficient varies over 0.15 to 0.3 for different land uses, but in our final application we will use a runoff coefficient value of 0.22. Next, we need to calculate the rainfall intensity, which obviously we have to use the given intensity duration curve relationship, which is given here. Now, recurrence interval is already given to us in the problem, but we need to determine the time of concentration of the watershed, and as we mentioned that there are several methods, but the Kirpich formula is the most popular formula for determining recurrence interval, and as per this formula, TC is 0.01947 L to the power 0.77 S to the power minus 385, where L is the flow length, S is the land slope or the watershed slope, and these are in L is in meters and TC is given in minutes as per this Kirpich formula. So, the maximum length of flow value is already given in the problem. It is 2.5 kilometers. So, we convert it to meters, it comes out to be 2500 meters. The elevation difference between the remotest point of the watershed and the outlet delta H is given as 25 meters. So, obviously, the slope will be calculated by this ratio delta H by L. So, from here we get the slope of the watershed as 0.01. And thus, we can calculate the time of concentration because we know the L, we know S. So, by putting these values of L equals to 2500 and S equal to 0.01, we get a value of TC as 47.4 minutes from the Kirpich formula. And now, we know the return period and also the time of concentration we have determined. So, that means the recurrence interval is 20 years and time of concentration just now we determined 47.4. So, obviously, using the rainfall intensity duration frequency relationship which is given here. So, by putting the value of T equal to 20 and TC equal to 47.4, we can get the value of intensity which comes out to be 283.32 millimeter per hour, or because we want in meters per second. So, we convert that to 7.9 into 10 power 5 meters per second. The total area of watershed is the sum of land uses in three categories, which comes out to be 5.4 square kilometers or 5.4 into 10 to the power 6 square meters. So, now we know C, we know I, we know A. That means we can put the values in the rational method, rational formula QP equals to CIA. C we calculated earlier at 0.22, and these values I and A values are already there in front of us. So, this is I, this is A, and then simply we get QP value of 93.9 cubic meter per second. That is the discharge, the peak rate of runoff from the watershed is 93.9 cubic meter per second with the given information. That is the final answer of this particular question. Then we go to example number 4. Again, we still remain in rational method, another variant of this particular problem. So, that is the maximum rainfall with a return period of 5 years is given below for a watershed having a time of concentration of 47.65 minutes. So, we have been given time of concentration, and maximum rainfall of return period of 24 hours is given for different durations, like you see duration and depth of rainfall. So, duration 10 minutes, 20 minutes, 30, 40, 60, and we have depth of rainfall is 52.5, 55, 57.5, 60 and 65. So, this information is already provided to us. In this watershed, 2 square kilometer area has been cultivated over sandy soil, where C value is 0.2, and the remaining 3 square kilometers has been cultivated over clay soil, where C equals to 0.7. Determine the peak rate of runoff for this watershed, and this question has been taken from GATE 2007 question paper. So, of course, we have been given time of concentration here. And also we have given for different duration what is the depth of rainfall. So, obviously, using these three information, we have to determine the maximum depth of rainfall that would occur over this time of concentration of 47.65 minutes. And obviously, I have just used the truncated table here because our time of concentration lies between these two, 40 and 60 minutes. So, of course, we have to have the linear interpolation here. So, we will use 40 and depth of rainfall 60 as the base value, that is which is here, and then we will know that over these 20 minutes the rainfall is 5 mm. So, that means 5 by 20 multiplied by 7.65. So, that means we will get the maximum depth of rainfall for 47.65 minutes duration as 61.91 millimeters, which is of course in between these two values, as you can see, which is expected also. Now, we know that for given duration, what is the depth of rainfall? So, we can find out the rainfall intensity. So, rainfall intensity will be 61.91, which we calculated, divided by the duration 47.65, and of course, multiplied by 100 in order to get the value in millimeter per hour. So, it is 77.96 millimeter per hour, but because we use in meters per second, so that is why we are converting that and we get a value of 2.17 into 10 to the power minus 10 to the power minus 5 meter per second is rainfall intensity. Now, we have also been given two land uses. Where 2 square kilometer under C value of 0.2 and 3 square kilometer under value of 0.7, that is 2 cultivated area with C and 3 square kilometer cultivated area C equals to 0.7. So, obviously, we have to use the weighted runoff coefficient here and we get the value of 0.5 by putting in this formulation. And area is given as 5 square kilometers. So, obviously, in square meters we convert 5 into 10 to the power 6 square meters. So, now we know C, we know I, we know A. So, we can put in the rational formula QP equals to CIA 0.5 times 2.17 times into 10 to the power minus 5, which is here, times 5 into 10 to the power 6, that is the area here, and then the QP value comes out to be 54.25 cubic meter per second. So, from this for this problem, for the given data, the QP value comes out to be 54.25 cubic meter per second, but here we saw that we needed to get the depth of rainfall corresponding to given time of concentration from the given data. So, this is one variation of the problem which may be asked in examination. Now, we go to next example where we start with SCS curve number method. Example 5. A watershed with various land usage as specified in the table here receives a rainfall of 152.4 millimeters. If the initial abstraction is 0.2 times the potential maximum retention, the antecedent moisture content AMC of average condition is assumed. Then find the depth of runoff volume in millimeters. So, almost all the information is given here. And you have land use, percent land use, 40% under residential, 25% under open space good condition, 20% under commercial and business, and 15% industrial. And soil groups also, in two cases it is soil group C, in two other cases soil group D, and the applicable curve numbers are also given here. And this question is taken from GATE 2022 question paper. So, in this case, as per SCS curve number, we know the depth of volume, runoff volume, that is runoff volume is VQ equals to P minus 0.2S square plus P 0.2S. Of course, it assumes the initial abstraction IA equals to 0.27. Here P is the mean precipitation over the drainage basin, S is the maximum potential retention of the water by the drainage basin. So, this formulation already we have seen. And of course, we also know that if IA is not equal to 0.2S, this is simplification has been brought by assuming that IA equals to 0.2S, then we can use this raw version of this formula where in terms of IA and S. So, if IA could be other than 0.2S, then we can of course manipulate this formula accordingly. So, maximum potential retention is related to curve number, already we know by this relationship, which will give us S in millimeters. Now, since we have multiple land uses of watershed, Here same table is reproduced and with different curve numbers. So, we have to obviously use the weighted curve number and this same formulation which we used for runoff coefficient earlier, similar formula we have to use. So, of course, it is already given in percents. So, 0.4 into 83, that is the value for residential area, 0.25 into 80 for open spaces, 0.2 into 94 which is for commercial and business, and 0.15 which is 15% area, that is 0.15 into 93 which is for industrial area. So, we get weighted curve number of 85.95. And once we know the curve number, we can determine S using this relationship, and by putting the curve number of 85.95, we get potential maximum retention is 41.52 millimeters. And we already know that IA is given as 0.2s and rainfall depth is 152.4 mm. So, obviously, we can use, because it is IA equals to 0.2s, so we can use straight this formulation. That means, if we have to just put the value of P and value of S here, P value is given already given, S value we have determined. So, by beating this value, we get the runoff depth volume which comes out to be 111.86 millimeters as per SCS curve number method. So, this is one application of SCS curve method for a given problem. Then we go into example 6, and this example says that a small watershed receives rainfall of 90 millimeters in a day. For this watershed, irrespective of land use, the amount of initial abstraction can be considered as 25% of potential maximum retention of soil. So, here you see there is a variation, it is IA is not 0.2s but 25% or 0.25. Initially, the entire watershed was under forest with S equal to 136 mm, which was converted into cultivated land with S equals to 64. Find the change in daily runoff volume due to this land use alteration for this specific rainfall event in percentage. And this question is from GATE 2021. And as you can see, the municipal potential maximum retention for the forest and cultivated lands are given. So, S forest, just for distinction we are writing S forest as 136 mm and S cultivated land is 64 mm. Rainfall depth is given as 50, P equals to 90 millimeters. And IA is given as 0.25s. So, that means we have to use the original formulation P minus IA. So, also putting IA equals to 0.2s, we can get in terms of S, this is the formulation. So, instead of calculating IA separately, we are just manipulating this formula. So, it becomes P minus 0.25 S square by 2P plus 0.75 S. Now, we know the value of P and we know the value of S for forest as well for cultivated land. So, we can calculate runoff depth volume for both types of land uses. So, VQ forest by putting the values of P and S forest, we get a value of 16.33 millimeters. And the daily runoff volume for cultivated area. Again, for cultivated area, we have to change the value of S, which is 64 against 136 here. So, we get a value of 39.68 millimeters. Thus, the change in daily runoff volume due to land use alteration is, of course, in forest case it was 16.33, now it is 39. So, it is quite expected that if land conversion is there from forest to cultivated land, we will get higher runoff. So, that is why the percentage change, there is an increase in runoff volume, and that is 143% increase. So, there is an increase of 143% in daily runoff volume due to land use alteration, that is from forest land to cultivated land. Runoff goes up by 143%. Now, we get into example number 5 and example number 7, sorry. Again, we are with the SCS curve number method. So, for a 39 square kilometer area, the curve number under AMC2 condition is given as 74. Find the change in runoff if the condition changes from AMC2 to AMC3 for a rainfall event of 45 mm. So that's the problem. And coming to solution, we have been already given Cn under AMC2 condition is 74. So Cn AMC2 is 74. And thus the Cn under AMC3 condition can be calculated. We already saw that we have both table as well as direct formula. So we can use the formula where Cn AMC3 is related to Cn AMC2 in the following form. And then we knowing Cn AMC2, that is curve number for AMC2, which is 74, we replace in this equation or substitute in this equation. So we get 23 times 74, 10 plus 0.13 times 74, and the curve number for AMC3 comes out to be 86.75, higher because we remember that AMC2 condition is the average condition, whereas AMC3 is wet condition. That means we will be having higher runoff in this case because already wet condition is there. So for AMC2 condition, the potential maximum retention S2 is we are using this relationship. We know the curve number value. So this value comes out to be, by putting the value of curve number AMC2, we get is 89.24 mm. And similarly for AMC3 condition, the potential maximum retention S3 is by putting these values AMC3 of 86.75, we get S3 value as 38.79 millimeters. So both the conditions we know the S value or potential maximum retention. Now runoff for AMC2 condition, because we know already S value. So using this formulation, we also know that I is 0.2S. It is given already in the problem. So using this formulation, by putting the value of P and value of S, we can calculate the value of VQ, which comes out to be 6.33 mm. That is when AMC2 condition is there in the watershed. If when the condition changes to AMC3, then again we have to use this relationship. The value of S in this case will be different, and it is now we are using a 38.79 and it comes out to be 18.24 mm. So from 6.33 mm to 18.23, that means there is a increase in runoff which is expected because of the wet conditions in AMC3. Hence, the change in runoff we can calculate is VQ3 minus VQ2 by VQ2, because with reference to VQ2 we are calculating, that is why denominator is VQ2, and that is why we find that there is a positive value, that is 188.15%, which shows that there is an increase of 118.15% in the runoff volume due to change in the AMC condition. So this is yet another variation of SES curve number problem. Of course, the concepts remain the same, but the variations could be different. So now we take the last problem, that is a 10 hectare watershed received 100 mm uniformly distributed rainfall. Land use pattern consists of 25% residential area with soil group C and curve number 82. Good meadow condition at 50% of area with the soil group D and curve number 78. There is also good open space condition in 25% area with soil group D and curve number 80. Assuming AMC2 condition, find the volume runoff in cubic meter from the watershed, and this question has been taken from GATE 2009. So of course, we know that procedures by this time, when there are multiple uses, land uses, multiple conditions, then obviously the curve numbers will vary. So we have to, in that case, we have to first calculate the weighted curve number. In this case, we have three different conditions. So it is given clearly that 25% area has curve number of 82 here, 50% area has curve number of 78, this is here, and remainder 25% of area has a curve number of 80. So it is here. So the weighted curve number we get is 79.5. So this is the curve number we get. So obviously once the curve number is obtained, next thing we do is obtain the potential maximum retention of the watershed using this standard relationship. So by putting the curve number as 79.5, which we have determined, we get a value of 65.5 mm. That is the potential maximum retention of the watershed. And Considering IA equals to 0.2s and rainfall value of 100 mm, which is there, the depth of runoff volume will be by this standard relationship where IA equals to 0.2s already put, and then putting the value of P and equal to 100 and S equal to 60.15, we get VQ equals to 49.55 into 10 to the power minus 3 cubic meters. The area of watershed is 10 hectares, that is 10 to the power 5 square meters. So, the volume of runoff from the watershed V equals to A times VQ, which is in depth units. So, total, because we have to give answer in cubic meters. So, that is why the volume of runoff from the watershed in volumetric unit is 4955 cubic meter. So, we saw that different variants of problems we have seen for Cook's method or rational method or SCS curve number method. And I am sure that with the theoretical background we discussed in previous lectures, you will be able to solve problems. Of course, you have to practice more number of problems to be efficient, so that you can solve it at a faster pace. Please give your feedback and also raise your doubts or questions, which we can answer in the forum. Thank you very much.